Okay, we are going to look in this video at stoichiometry of gases. Now remember, for stoichiometry, we are looking at relative amounts of chemical reactions. And when we were looking at the gas laws, one of them had moles in it. Hey, if we can react, if we can have moles, we can do stoichiometry. So I want to look at a gas reaction that is kind of important. Which is the formation of ammonia gas. Let me get my marker to work a little better here. So if I combine nitrogen and hydrogen, I get ammonia. Now, let's look at this stoichiometrically. If I take 1 liter of nitrogen, how many liters of ammonia am I going to get if I am at STP? Well, this one is kind of nice because I can use Avogadro's law. And I'm going to use a different number. Instead of 1, I'm going to use 14.0 liters of N2. Okay. And I know that there are 22.4 liters in 1 mole of N2. And I know that I get 2 moles of ammonia for 1 mole of N2, and ammonia as a gas also has 1 mole. I didn't do this very good. There are 22.4 liters of ammonia in 1 mole. Now, I made a mistake here. I didn't intentionally make a mistake, but I did, and you can figure it out, because if I look here, liters of N2 and moles of N2 are not going to cancel. So if you write their units out every time, like I say to, and you make a mistake, you will catch it. This is wrong. This is not written correctly. I need to put the 22.4 liters of N2 on the bottom, 1 mole of N2 on the top. And when I multiply this out, you know what's nice, this number cancels. I can do this math in my head. This gives me 28.0 liters of NH3. Very simple, okay? All right, you might hear some noises in the background. That's okay, my kids are helping here. So taking a look at this one, I've got 28 liters of NH3. What would happen if we weren't at STP? Well, if we're not at STP, but the conditions are constant, these two values won't be 22.4, but they will be the same number. The only time it's different is if I change conditions. Okay, so if I have one at STP and one is not at STP, I'm going to have to use the ideal gas equation and find moles in a different way than using Avogadro's law here. So that's one of the things that we can do. The other thing we can take a look at is I can look at the ideal gas equation. So let's say I have a very simple reaction. I'm going to take some sodium carbonate and react it Okay, so you can't read that very well on the right here. That's okay. This is, let me see if I can do it better. It's NaCl, okay? And when I balance this reaction, I need 2 of these here. But what's important, I have here. Now, let's say I have 10.0 grams of sodium carbonate. How much carbon dioxide am I going to get? What volume if the temperature is equal to 25 degrees Celsius and the pressure is equal to 1.02 atmosphere? Okay, what volume am I going to get? Okay, well, this is a relatively simple problem. Again, I say simple, I don't say easy. That just means we don't have a lot of steps to it. Well, the first thing I need to do is I need to take my given amount and convert it to moles. So I have 10.0 grams of sodium carbonate. And knowing the molar mass of sodium carbonate, let's see, oxygen is 16, 16 times 3 is 48, plus 12, that's 60. 60 plus 23 and 23 are 46, 106.0 grams. And this is going to give me moles. I'm just going to write moles here. So that's going to give me moles of Na2CO3. And I can take the moles of Na2CO3 times 1 mole of CO2 per 1 mole of Na2CO3. So this is going to give me my moles, okay? Again, I'll do this a little bit to where you can see it. So this gives me, when I'm done with this, moles of CO2. Notice that I've left the button punching for you, but I'm going to go ahead and do that right now because I need this number for the next step. So I'm going to really simply take my calculatorial device and take and find that I get 0.0943 moles. Okay. Now, I would just keep going on the board, but I've kind of run out of visible space here. So I'm going to go ahead and erase this work, which you already have. You can rewind it if you need it. Okay. And now I have moles of CO2, and I have the equation PV equals nRT. That's simple enough. What am I looking for? V. V is equal to nRT over P. Now I just solve for my moles, 0.0943 moles. My R, I could use the 8.314, or this is in atmospheres, 0.08206 liters atmospheres per mole. Okay. Okay. And my temperature, 25 degrees Celsius. This gives me 298 Kelvin. Yes, 25 degrees Celsius has 2 significant figures, but when I add 273 to it, that's addition. This is to the unit, the 273 is to the unit, my 298 is significant to the unit. I now have 3 significant figures here. And when I divide this by my 1.02 atmospheres, I have a very simple problem here. And I get 2.26 liters. Very simple. I can solve the problems like this. So I can either use the ideal gas equation and go into and out of moles using the ideal gas equation, or if it's an STP, I can use 22.4 liters per mole if the if the conditions are constant, if pressure and temperature don't change, the volume is a direct measurement of the number of moles, and I can just go from volume to volume. And this is our gas law stoichiometry.